Here's your second video on section 4.2, which will be talking about Newton's first law of motion and Newton's second law of motion, which is F equals ma. Newton's first law, by definition, now that you're in a physics classroom, is a little bit longer, a little bit more involved. It says an object at rest remains at rest, and an object in motion continues in motion with constant velocity in a straight line unless it experiences a net external force. So you're traveling down the road and something hits your car, right? So that would be an external force that is hitting it. It is also known as the law of inertia. So another name for Newton's first law of motion is the law of inertia. Please make sure that you know that. Another name for Newton's first law is the law of inertia. Check out this flow chart, guys. If the forces are balanced, okay, if your F net equals 0 newtons, okay, so in other words, either the object is at rest, and if the object is at rest, then your velocity is 0. Well, if your velocity is 0, then your acceleration is 0. Well, if your velocity is 0 and your acceleration is at 0, your F net is 0, which means you're staying at rest. But what if the object was in motion? Okay, if the object is in motion, that means the velocity is some non-zero object, or I'm sorry, non-zero variable quantity, in other words. Now, look at this. It says acceleration is 0. Ooh, tricky, tricky. To get your acceleration to be 0, your velocity has to be a constant in velocity, i.e. cruise control is set. Because think about it, once again, you're driving down the highway, you got your cruise control set. Are you pushing the accelerator at all, or the decelerator, i.e. brake pedal at all? No, you're not. So you're not changing your velocity, but it is some non-zero number. Make sense? So you're going to stay in motion at that non-zero number unless you're acted upon by some net external force. Got it? Okay, read the little owl here. It says the objects keep doing what they're doing. That's just the summing it up of Newton's first law. I like that. It comes from physicsclassroom.com. You'll see a lot that refers to physicsclassroom.com on forces. Please make sure if you ever have any downtime that you are looking at that site, especially underneath the forces section. Okay, moving right along then. Next thing here, predict what will happen to the passenger of the toy car once the car hits the wall, if the car continues to move forward. Well, if the car is moving forward and the passenger is moving forward, what would happen to the passenger if the car has to stop once it hits this wall right here? The passenger is going to try to continue to move forward. Why would the passenger continue to move forward? Because of Newton's first law, right? The object in motion wants to stay in motion. Okay, here's the cool part. Unless acted upon by an unbalanced force, what are you to be wearing every time you get into a car, regardless if you're in the front seat or the back seat, driver's seat, passenger seat, behind the driver, behind the passengers, in the middle, whatever. You should have your seatbelt on, right? That's going to be opposite direction of motion. It's going to hold you into place. Please make sure I can't click on this while I'm recording, or else I would. Please make sure that you look at this scenario with the truck with the ladder on top of it on what happens when the truck slams on his brakes and the ladder is not securely attached to the top of the truck. Okay, moving right along then. Inertia. For an object to have inertia, you need to know this definition. It is known as the tendency for an object to resist change in motion. Mass, mass, mass is inertia's best friend. They are best friends. If you have a really big mass, you got a ton of inertia. If you have a small mass, you got a little bit of inertia. Okay, can you calculate inertia? No. Inertia is not a calculated value. Therefore, inertia does not have any units. It is the mass that you are assessing when you talk about how inertia-esque this system is, or this object is. Continue with that idea. It says the inertia of an object is proportional to the object's mass and indirectly related to its acceleration. Therefore, more mass means more force needed to change the motion. Why? Because it has more mass to it. Therefore, direct relationship there. What are they pulling from here? Right? Look at this statement right here. So I want you to think about, technically I want you to think about F net equals ma net. So if you're thinking about this, you should say the more mass, the more force, because they are directly related to each other if you're moving at a constant velocity, i.e. utilizing Newton's first law of motion, which makes sense then, right? So inertia is not an example of a force. You need to know this too, because that is an awesome multiple choice question. So make sure you're aware of that. Okay, next one. What changes inertia? inertia. What changes inertia is an addition of a force. That additional force is called friction. Friction works opposite direction of motion. You need to know that. Friction works opposite direction of motion. So on a free body diagram, force of friction would be opposing applied force. Okay, and they're usually going to be horizontal. They're usually going to be F net x equals, and that's when you would talk about your applied force and your frictional force, F net of x, applied force and frictional force. Okay, so it used to be thought that it was the absence of a force that caused an object to stop moving and to come to rest. It's now determined that it is the addition of a force that causes an object to come to rest, and that additional force is friction. Okay, so you're sliding your physics textbook across your desk. It comes to rest, right? Because of your coefficient of friction, which we'll get there. Each surface, tile, carpet, whatever, has a different coefficient of friction to it. And it's telling you how friction-full or frictionless an object or a surface in this case is. So like your desk has some friction on it. So as you slide that book and you leave go to it, it's going to eat up friction. It's going to eat up the applied force, therefore causing the object to come to rest. Okay, mass and inertia. Mass is that quantity which depends solely upon inertia. So here's some examples of this. You have so many books on your head. You hit the hammer, it's going to be absorbed. That contact impact is going to be absorbed by the book so you don't feel it on your head. It's the same analogy of like putting your hand down on a desk and a book on top of your hand and then a sledgehammer down onto it. You don't break your hand. Okay? Don't do that though. Don't do it. Okay, a more massive object has a greater tendency to resist change in its state of motion. So here are several examples on this slide. Please click on that link there and read through those different examples. Here's yet another example. You have a 10-kilogram bowling ball and a 5-kilogram basketball. They're both initially at rest, so their acceleration is 0, right? Well, if their acceleration is 0 and you're using the equation F net equals ma net, whereas velocity equals 0 meters per second, therefore acceleration equals 0 meters per second squared, then what you're really looking at is the relationship between these two variables, which is a direct relationship. So, which object has greater inertia? The object with more mass will have greater inertia because mass and inertia are best friends. Okay, so the 10-kilogram bowling ball would have more inertia than the basketball because it is heavier, more massive. So summing it up, using your equation, F net equals ma net. How are mass and inertia related to each other? Directly. Try answering these before I write them down, guys. See if you're right. How are mass and acceleration related to each other when force is held constant? So with a constant force, how are mass and acceleration related to each other? Indirectly. How are force and acceleration related to each other when mass is constant? Force and acceleration, they would be directly related to each other. What is the object doing when mass is constant if there is a force present? And let me be more specific. So your F net does not equal 0 newtons. It equals some value. So it is in motion. Use your physics terms. Don't say it's moving. All right? That's layman terms. You want to be specific here. So in motion. Object is in motion. What is the object doing when mass is constant if the force value is 0 newtons? One of two things, and I apologize that it's cutting off the bottom here, but it's either at rest, and that is because velocity does equal 0 meters per second, or it is moving at a constant velocity. And if you're moving at a constant velocity, your acceleration is 0 meters per second squared. Same thing up here, guys. Your acceleration would be 0 meters per second squared if your velocity was 0. That should make sense. Okay, net force, sum of all forces put together. So draw and label a free body diagram, take direction and magnitude into consideration. If the vector sum equals 0, the object must be moving at a constant velocity. If you have no acceleration, then you have no force sum. Equilibrium means balanced forces and objects that are either at rest or moving with constant velocity. So equilibrium is two scenarios here, either objects that are at rest or objects that are moving with a constant velocity. So let's look at this sample problem. Derek leaves his physics book on top of his drafting table that's inclined at 35 degrees. Draw the free body diagram and calculate the net force on the book when it experiences an F of G of 22 newtons, an F of N of 18 newtons, and a frictional force of 11 newtons. You want to know what F net equals in newtons. So 35 degrees, your F of G acts straight down. Your F of N is to the plane. So the direction of motion would be down the plane, right? So F of F is going to be headed this way. Making sense? Okay, so with that in mind, we're going to then have to break this down and turn it over to say, this whole thing's going to rotate this way, okay? So we're just going to rotate this around. Well, if you rotate that around, your F of G is now right here. So you have an FG of Y and an FG of X. There's your theta, right? So your FG of Y, your F of F, your F of N, and your FG of X. So we need to solve for FG of X. FG of X is going to be F of G times, well, how's it working, guys, in relationship to theta? This is an example of an hourglass triangle. So your FG of X is going to be sine theta. Whereas your F of G is 22, sine 35. Make sure you're in degrees and not radians. That's going to give you negative 13 newtons for your FG of X. Your FG of Y is now adjacent. So FG of Y is going to be F of G cosine theta. And I'm going to skip a line here because of space. But that would be negative 22 times the cosine, right? Negative 22 times the cosine of 35, which is going to equal negative 18. So FG of Y equals negative 18 newtons. Let's insert a new page here and finish this guy. Okay, so your F net in the X direction is going to equal your force of friction minus your FG of X, which your force of friction was 11 minus, and that was 13. So your F net in the X direction is going to be, let me correct this, guys, it's plus, it's net. So that's plus, that's how I got the negative, because it's 11 plus a negative 13. Okay, so F net of X is negative 2 newtons. F net of Y is going to be F of N plus F of G, which is really F of N minus F of G. F of N was 18 newtons, and F of G was 22 newtons. So your F net in the Y direction is going to equal, oh, I apologize. This should be FG of Y, which was also 18. So your F net in the Y is 0 newtons. So then putting this all together, your total F net then is F net equals F net X plus F net Y, which equals negative 2 plus 0, negative 2. Therefore, F net equals negative 2 newtons, right? No sig figs. Okay, so the real final answer is F net equals, how many sig figs from your givens, guys? 2 sig figs, so it should be negative 2.0 newtons. That's your final answer that you need to box for this problem here. Very good, very good, very good. Okay, so this is going to start off Newton's second and third law, which we're not going there. So now you want to just do practice B problems that are just like this on your textbook. Great job, guys.